Producing Street Talk for all this time now has given me a deep interest and understanding of what it means to think and what it means to be intelligent. Machine learning systems typically learn to approximate functions by relating input variables to output variables in a process that Judea Pearl has likened to curve fitting. Programmers, on the other hand, define their algorithms independently of training data, purely in terms of operations over variables. The programmers have confidence that their programs will work in almost all situations. Humans can pick up new skills and assimilate new knowledge with a small amount of new information. This is the so-called kaleidoscope effect, which is to say, being able to cast previous experience into many new types of situations in experience space. We do this by building new models on the fly, by extrapolating from abstract prior knowledge. Coming up later on in the show.
60 minutes where you're going to try to catch us out and prove that we secretly bugged Jeff Hinton's house.
What's kind of a workable definition of abstraction? Going also here beyond the buzzword of, we need abstraction. I do abstraction, you do abstraction. Like, when does a system do abstraction, and what would you accept? Like, if I came to you and said, I have GPT-4 and it does abstraction, what would you accept as a test that is happening?
Professor Gary Marcus says, we want artificial intelligence we can trust in our homes, on our roads, in our doctors' offices and hospitals, in our businesses and in our communities. Robust artificial intelligence, while not necessarily superhuman or self-improving, can be counted on to apply what it knows to a wide range of problems in a systematic and reliable way, synthesizing knowledge from a variety of sources such that it can reason flexibly and dynamically about the world, transferring what it knows in one domain into another context, in the same way that we would expect of an ordinary adult. If we cannot count on our AI to behave robustly, then we shouldn't trust it. Gary concedes that we're missing some fundamental ideas about how to deal with the combinatorial complexity of reality and how to integrate knowledge that we have about the world with learning. We use a lot of abstract knowledge all the time, but all of the intelligent systems which have been created to date are narrow, which is to say there's almost no adaptation to novelty. Imagine a chess algorithm that broke if you changed the board size by 1 without having to retrain it from scratch. All of the latest efforts from DeepMind would fail on this simple hurdle. I think Gary really nailed it when he said transferring what an AI learns from one context into another. This is the fundamental thing which AI systems today are missing. Professor Gary Marcus is a cognitive scientist. He views cognition as a kind of cycle. Humans take in perceptual information from the outside. They build internal and possibly incomplete cognitive models based on their perception of that information, and then they make decisions with respect to those cognitive models. Gary passionately believes that if we don't do something analogous to this, we won't succeed in our quest for robust intelligence.
So I was brutally, repeatedly, frequently attacked for saying that these systems don't abstract very well, that there's a real problem with extrapolating beyond the training data, that replicability was a problem, that there's no real semantics there, etc. I think all of those are now actually received wisdom. They're now, in fact, if you watch Bengio's recent talks, they're basically the introduction to his talks are those things that I said. And LeCun has turned around, even he has actually turned around, and he's the one who brought to the world's attention the GPT-3 suicide example. So even like my fiercest critics have actually turned in the last couple of years. Yannick said it kind of amused me a minute ago. It's easy to make the argument about semantics. Well, no, it wasn't. For 20 years, every time I made it, I was accused of being a terrorist and a bad person. Whatever.
Gary advocates for a 4-step program, the initial development of hybrid neurosymbolic architectures, followed by construction of rich, partly innate cognitive frameworks, and large-scale knowledge databases, followed by further development of tools for abstract reasoning over such frameworks, and ultimately more sophisticated mechanisms for the representation and induction of cognitive models. He thinks that effective cognitive architectures are likely to look more heterogeneous with specialized modules. He also thinks that we're going to have to redefine what we even mean by learning. He thinks the new modality of learning is more abstract. It will include more language-like generalizations and would be relative to knowledge and cognitive models, incorporating reasoning as a first-class citizen in the process. He thinks that we've just been skipping too many steps. We need to start with a bedrock of cognitive primitives like operations over variables and attention mechanisms, and then we need to learn to recombine them. Gary says that the knowledge gathered by contemporary neural networks remains spotty and pointillistic, arguably useful and certainly impressive, but never quite reliable. Gary says that common sense is open-ended. Winning at a game of Go is entirely different to solving an unexpected planning problem in self-driving. I'm sure that Gary would say that self-driving car research has been an egregious waste of time and money. It's almost criminal. Gary also cites the lack of robustness of neural networks in respect of their training regime. Most human learners learn the same knowledge and language despite highly varied circumstances. Neural networks are sensitive even to the order in which the information is presented and many other features of the training regime. There have been some really cool ideas lately in the neural network space, but Gary thinks that stronger medicine may be needed to acquire, represent, and manipulate abstract knowledge, and to use that knowledge in the service of building, updating, and reasoning over complex internal models of the external world. Also joining us this evening is Professor Lewis Lamb, perhaps the most recognizable name in the neurosymbolic space. Lewis thinks that we can integrate logical reasoning and neural networks. He thinks that we can learn discrete structures and thus we can combine the symbolic and connectionist worlds. Lewis is a huge advocate of relational learning, although discrete relations lead to gradients, which are not easy to deal with in neural networks. Lewis points out that there are already hybrid models everywhere in production. Look no further than Google Search, for example. Lewis argues that we need abstraction, we need interpretation, and rigorous semantics as a foundation, instead of just focusing on these shallow correlations. He says that formalizing core knowledge is still a very open problem in the field. Lewis has done a lot of really cool work with graph neural networks, by the way. He's also concerned about these tribal divisions in the machine learning space at the moment. Do you remember Pedro Domingos? He spoke of the 6 tribes in artificial intelligence. Well, it was actually 5 tribes. I took the liberty of adding cybernetics as the 6th myself. Unfortunately, a lot of this conflict is born out of competition over obtaining grant money and powerful positions.
All this formal background is in symbolic AI. You cannot ignore that. When you look at the history of computer science, as Gary said, even McCulloch and Pitts, when they provided perhaps one of the first neural network models, one of the things that they showed in the paper was how this kind of networks they proposed carried out Boolean reasoning, logical reasoning.
Gary Marcus and Lewis Lamb think that we can address the current problems in AI using a modern set of techniques. They think that we can retain the benefits of deep learning, but again, promote rich cognitive models to be first-class citizens like they once were. These days, the focus is primarily on learning with these continuous geometric models, but Marcus and Lamb think that it must be part of a broader coalition, which is amenable to symbols, core knowledge, and reasoning. There is simply something profoundly missing from deep learning right now. Even the most sophisticated natural language processing models fail to demonstrate a scintilla of understanding. We need systems that do more than dredge immense datasets for subtler and subtler correlations. In order to do better and to achieve safety and reliability, we need systems which have a rich causal understanding of the world, and that needs to start with an increased focus on how to represent, acquire, and reason with abstract causal knowledge and detailed internal cognitive models. Gary says that it's a fallacy to suppose what worked reasonably well for domains such as speech recognition and object labeling, which largely revolve around classification, will necessarily work reliably for language understanding and high-level reasoning. Deep learning models fail to represent the richness of the world and lack even any understanding that an external world exists at all. My main observation is that both of these gentlemen are far more moderate than I would have expected. They both seem to be advocating for a hybrid approach, but with connectionist models as the first-class citizen. The main reason for this seems to be the learning which is enabled with stochastic gradient descent. This is the best thing about neural networks. The thought of exhaustively searching a discrete program space is enough to put chills down even the most hardy spines. Personally, I'm quite excited about the work that Josh Tannenbaum has been doing, going completely discrete first, and searching in this type 2 space. My worry is that combining symbols with neural networks, or a so-called subsymbolic or neurosymbolic approach, might mean that we end up with all of the problems that we had with symbol systems and lose many of the benefits. We already know from Chollet that neural networks are only capable of type 1 or interpolative generalization on a learned smooth manifold. They cannot perform type 2 or discrete or extrapolative generalization. These models do seem to allow us to represent and embed discrete data in a learnable continuous model, but what happens then? Do we lose the ability to reason? Unfortunately, once you project data into a vector space, it's irreversible and undecidable. Now, a few commentators said that there was an astronomical amount of jargon in the last episode. It seems to be increasing with compound interest, and this show might possibly be the worst ever. So we're going to try and explain as much of it as possible. A couple of years ago, Professor Marcus and Professor Bengio had a really famous debate where they battled horns. It was the symbolic approach versus the connectionist approach. It even spawned this interesting article called Marcus versus Bengio, the AI debate. Gary Marcus is the villain we never needed.
I think that we both think the other side is strawmanning our baby. So I think you're strawmanning symbols because lots of people put probabilities and uncertainty into symbols. I would argue that the kind of deep learning stuff that was straight out of the 80s, which is continued until like 2016 in my view, but we could argue about that. Just let's have a big multi-layer perceptron, let's pile a lot of data in and hope for the best, which I don't think you believe anymore, but maybe you did at one point. That's one kind of deep learning. That's the kind of prototype or canonical version of deep learning, and you want to open deep learning to a whole lot of other things, and I think at some level that's fine, and at some level I think it's changing the game. So I want to expand the umbrella of symbols, and you want to expand the umbrella of deep learning. Why don't we say let's build deep learning symbolic systems that expand the scope of deep learning and expand the scope of symbol systems?
Look, I don't care about the words you want to use. I'm just trying to build something that works and that is going to require a few simple principles to be understood. Neuroscientists have been talking about neuromodulators forever. So just remove from your brain the idea that deep learning is a 1989 MLP with feed-forward connection. That is not deep learning. Sorry. And I do agree that there's lots of interesting inspiration we can get today in the work that's been done in cognitive science and in symbolic AI.
Whenever we discuss symbols or symbolic approaches, think of traditional programming code with variables and loops. It's kind of like what powers the world's infrastructure already, right? Deep learning models deliberately eschew traditional programming, even though all the greatest technological achievements of mankind have relied on software utilizing symbolic computation. Deep learning has set the standard for learning from data, but it is symbolic methods which have set the standard for representing and manipulating abstractions for discrete problems. You wouldn't be able to pass a Google interview, or one of my interviews for that matter, if you are not intimately familiar with symbolic approaches. But how can we combine symbolic knowledge with perceptual data? In the classical John McCarthy-esque world of AI, practitioners were only concerned with knowledge, internal models, and reasoning. But if you scan almost any of the modern day literature on AI, you won't detect a single iota of these ideas, not even a whiff. Of course, you can count on Francois Chollet and Christian Sergedi and Melanie Mitchell to bring up common sense and reasoning, but it really is slim pickings in general when it comes to citing rich cognitive models. GPT-3 is the statistical language model which perhaps most characterizes our move away from these classical AI ideas since the resurgence of deep learning in the last decade, as we discussed ad nauseum on our special edition episode on GPT-3.
But if you wanted to give medical advice and somebody tried to set this thing up as a suicide prevention counselor, then it's a tragedy, right? You know, there's an example out there on the web where someone asked GPT-3 or said, I want to kill myself. And GPT-3 said, I think that would be a good idea.
It doesn't have any common sense knowledge, no explicit cognitive model which could be updated, and it cannot perform any explicit, extrapolative, or abstractive reasoning. What that means is that it wouldn't understand what John had sour grapes actually meant. Do you remember Aesop's fable, in which a fox tries to reach some delicious grapes? When he failed, though, he declared that he didn't want them anyway because they were sour. This is a linguistic embodiment of the abstract mental category of situations featuring something that is the object of someone's ardor, but having proven out of reach is subsequently deprecated by the person who desired it. This abstract quality, often concisely called sour grapes, is potentially recognizable in thousands of situations, and this phrase could be thus used as the verbal label on any such situation. GPT-3 doesn't understand the structure or the semantics of this abstract category. Remember when we said that true intelligence is about casting previous knowledge and new information into new situations? The kaleidoscope effect, which Francois Chollet mentioned a few episodes ago. Let's go one step further in breaking down the jargon. The 6 most important words that you can wrestle with in today's conversation are intention, spelt with an S, extension, reasoning, knowledge, semantics, and understanding. Behind the scenes, we actually spent hours and hours debating the semantics of these definitions, which gives you some idea of how complex it is. Intention, spelt with an S, is the internal structure of an object. It describes all the aspects of some object, while the extension is just one attribute, usually the output. For example, consider the following 2 statements. The tutor of Alexander the Great maps to Aristotle. Or, the most famous student of Plato maps to Aristotle. They both have the same answer, or the same extension, but the intention is different. This is really important because in most cases, statistical models either ignore the intention entirely or only approximate a latent and brittle representation of it. The intentional attributes are the building blocks which can be used to extrapolate new knowledge and understand how a particular answer was derived. The intentional attributes are the core cognitive primitives required to construct and extrapolate new knowledge in future novel situations, given a tiny little bit of experiential information. Intention is about understanding the deeper reality so you can generalize it better. Extension is just the result of some computation, but we don't know how the answer was derived. Reasoning is the act of deriving new knowledge from prior knowledge, given new information using logical axioms and rules. For example, if I told you that my personal trainer had been milking me, you will reason that I've been spending too much money on personal training, or at least I hope that's what you will reason. It might just be simple deductive reasoning, or it might be abstract reasoning, which amounts to extrapolation. What about knowledge? Knowledge is a justified true belief. True means it's a fact. Justified means that it's been established or proven. This is distinct from data, which could be almost anything, and information, which is just curated data. Knowledge is the gold standard at the top of the pyramid. What about semantics? People often argue over semantics when they pick apart the meaning of an utterance to draw a different conclusion. If you try to get a clear definition of what semantics itself even means, you might have a fierce debate on your hands. Most people will tell you that it's only relevant in the context of linguistics, but that's not true. Semantics is about the interpretation of or mapping to an inner structure to assign meaning. Think of semantics as the raw building materials of meaning, the bricks and mortar. Almost anything can have meaning. An image, for example. Everything has an infinite inner structure or set of attributes. These are the bricks and mortar. For example, a string has a length. How many A's are in the string, or how many B's are in the string? Given a situation, you interpret the meaning of an utterance by selecting the relevant attributes, the relevant bricks and columns to construct your meaning. Any object has the structure or building materials which can be selected to build the interpretation or the meaning. The building materials and the possible meanings are both infinite. This goes back to Chomsky's conception of universal grammar. He said that everything is embedded in the structure. You can't get something from nothing. So syntax is the inner structure, semantics is the content, or what the structure is saying, or what it means. And for the sake of our purposes here, you can think of the syntax or the inner structure as being the same thing as the intention, spelt with an S. What about understanding? Understanding is successfully ascertaining meaning by reconstructing the original intention or that inner structure from the syntax and any prior semantics that we have. It allows the derivation of all of the possible new semantics. We understood what was presented if we can describe and reapply the knowledge gleaned. For example, the beer fell off a table and splashed on the floor. A person who understood that utterance could, from the semantic map of the sentence and probable world models, derive that now the floor is wet, the floor is slippery, and people might fall down on the floor. All of which are new semantic maps from those new sentences to an updated world model. Now, deep learning models, they don't explicitly learn the inner intentional structure, or not robustly. They do kind of learn it to some extent. They might have a latent dimension for fur on an animal, for example, but discrete problems or problems which require few-shot extrapolation or abstract or step-by-step reasoning are bad for deep learning because no smooth, learnable, latent manifold exists for these problems. Deep learning models can only generalize for interpolation on the surface of a learned, latent manifold, mostly representing the statistical regularities of the extensional answers, not the core building blocks or the semantics. Neural networks are giving you a fish, whereas semantics are teaching you how to fish. Now you see, I just used a metaphor there, didn't I? Metaphors are the cousins of analogies. It helped you understand, didn't it? By abstracting the information, I allowed you to apply your existing knowledge to a new situation in experience space. This is what we need AI systems to do, to reapply existing knowledge in future novel situations using abstract analogies. The only potential problem is that some analogies are cognitively laboring and they might not be understood by people. So there's always a balance of the information conversion ratio of an analogy and the reliance on common knowledge and cognitive processing on the other end to make sense of it. Now, the problem with language is we don't yet understand the universal, intentional, or primitive logical structural building blocks of it, not in a way which captures all situations. Does this lingua universalis actually exist? Surely it must do, right? The tragic thing for us is that a 4-year-old kid can extrapolate using language semantic primitives, but we haven't yet built an algorithm to do the same thing. I recently read an article on LinkedIn which highlighted the lack of understanding of intention versus extension by deep learning folks, in my opinion. Someone thought that they had used deep learning to learn the discrete Fourier transform. The discrete Fourier transform can be thought of as a matrix multiplication, where all of the cells in that matrix are a function computation. The computation is a complex exponential which deconstructs your signal onto the complex unit circle, representing integer oscillations of different frequencies using sines and cosines. If you visualize this matrix, it looks like a pretty picture which has all of these concentric and overlapping circles on it. So this chap formulated an optimization problem to learn the DFT by randomly initializing a matrix of values and optimizing with stochastic gradient descent on the squared loss of the real discrete Fourier matrix and his learned matrix. Surprise, surprise, it quickly converged to the values of the discrete Fourier matrix. Now, did this guy actually learn the Fourier transform, or did he just learn the values of the Fourier matrix? Because if you think about it, it was only learning the extensional answers. It wasn't learning the intentional structure of that discrete Fourier transform. The model has no idea how to rederive those values from first principles. This might be pointing out the obvious, but nothing the model learned could be used to help it learn a conceptually similar problem. So if we changed one of the coefficients on that DFT formula, even by 1, if we changed n by 1, then nothing it learned would be transferable, right? You'd have to train the model again from scratch. And this is exactly the same reason why GPT-3 doesn't understand how it arrived at an answer, and it can't abstractly reapply any of its knowledge in a new situation. So the main thing that these models are missing at the moment is the ability to abstractly reapply knowledge. This is really what we need. So the guy who wrote this article, he went one step further and he learned the Fourier transform via reconstruction, which is to say not using an explicit Fourier matrix even to test against, only testing using the squared loss of the original signal against the reconstructed signal. But when he reconstructed the signal, he basically used the sines and the cosines of the original signal to do so. So he biased the model by baking in the intentional knowledge and the Fourier transform into the optimization problem itself. So what would Rich Sutton say about that? He also unwittingly created a symbolic model. I think this misunderstanding is a pretty good analogy for what is going on in the deep learning space at the moment. Professor Rich Sutton said that we should finally learn our lesson and recognize the appeal of what he thinks are our mistakes, which is to say, building systems the way we think doesn't work in the long run. He thinks that building knowledge into our systems works kind of good in the short term, but reaches plateaus in the long term and actually inhibits our progress. He thinks that progress comes from scaling computation through searching and learning. Well, I think I agree with him, actually. I mean, if he's pointing out that our knowledge should not be handcrafted, then, God, yeah. In my opinion, this is the most obvious bottleneck imaginable. Every single time in my career when I've been working with human knowledge engineering, it's been a disaster. The term knowledge acquisition bottleneck was coined for a reason, in my opinion. Sutton is an anti-nativist. Anti-nativism is the theory that concepts, mental capacities and mental structures are not innate and required by learning. It's the ultimate belief in the blank slate, basically. An intelligent system is one which can dynamically and efficiently discover new knowledge through increasingly abstract analogies. The more of a conceptual stretch, the higher level of intelligence is required. Arguably, it's automated knowledge acquisition rather than Robust.AI, which is the biggest challenge that we have right now. A 4-year-old knows that the larger than relation is transitive. How is that? I think people misattribute the bitter lesson as being an argument for big data. Actually, it's an argument against human-crafted and human-introspected knowledge. The biggest knowledge base experiment to date is the Psych project created by Doug Lenat. It was started in the 1980s and it has over 1 million rules in an epic common sense knowledge base. Pedro Domingos referred to the project as a catastrophic failure. Even the most notorious GoFi advocate, Marvin Minsky, he concluded that for each different kind of problem, the construction of expert systems had to start over again from scratch because they didn't accumulate common sense knowledge. He said that unfortunately the strategies that were most popular by AI researchers in the 1980s had just come to a complete dead end. Sutton also points out that the actual contents of minds are tremendously, irredeemably, and endlessly complex. He thinks that attempts to model or conceptualize human minds using symmetries or objects or space or even multiple agents are flawed. He thinks that we should instead only build the meta methods to capture this complexity prototypically, which is to say, only in its potential. Critically, he thinks that we should build what we would call emergent AI, so it can discover like we can, rather than have us tell it what we think we have already discovered. So in some sense, I agree with Rich. I don't think we would understand the structure of an AI system any more than we would understand the workings of our own brain. But there's a good argument that common sense knowledge is or could be universal, so it seems pointless to relearn it from scratch every single time. What I think Gary Marcus is 100% correct on is that for us to create such an artificial intelligence on computers would involve symbols, discrete world models, and discrete extrapolation. But I think the answer lies in a modular architecture, which will likely be discrete first, in my opinion, involve neuro-discrete program search, and involve neural networks and other continuous models as perception modules. The system must also possess these meta-learning priors that Chollet mentioned in his measure of intelligence, allowing it to consume prior knowledge and derive new knowledge and reason over that knowledge. When a self-driving car arrives in a new city with a holiday parade, it needs to rapidly adapt to the new situation. Rich's Bitter Lake article might seem insightful at first, but there's not yet an existence proof of a reinforcement learning system which works well on open-ended domains, right? Which learns efficiently and which generalizes. Rich and his friends just released a new paper called Reward is Enough. The premise of the paper is that simply maximizing a reward, indeed any reward, given a sufficiently complex environment, is all you need to develop strong and general intelligence. In a similar vein to the bitter lesson, they think that the agent will learn all the skills it needs, even things like exploration and memory. It's all an extension of the idea that humans should not preconceive how they think intelligence should be architected at a high level. The root of why they can get away with shenanigans like this is their definition of intelligence is, in my opinion, wrong. Frankly, the paper would have been risible had it not been written by the godfathers of deep reinforcement learning. Their definition of intelligence doesn't even consider efficient abstract generalization or analogy making, which according to Douglas Hofstadter and Francois Chollet is the absolute core of cognition. This is a clip of Douglas Hofstadter talking at Stanford.
If we are going to make any connection between analogy and a geographical situation, we're going to liken it to the interstate freeway system, and it links everything together. Analogy is the interstate freeway system of cognition. It is not one little tiny zone somewhere off in the side. So that's a kind of a way of that I think about it. I mean, I don't really usually think about it that way. I made that up yesterday, so but it gives you the flavor. Categorization is the name of the cognition game, but analogy is the mechanism that creates or that allows categorization to happen. By categorization, I mean deciding what something is, what the essence of something is. Now, one could sort of summarize this in a corny little analogy. Again, analogy is the motor of the car of thought, and then we then can even write it down as this little thing. Analogy is to thinking as a motor is to a car, A is to B as C is to D. Analogy making is the perception of common essence between two things. And then a couple of footnotes to sort of hedge. I mean, things don't have essences, but what I mean, I'm not talking about some kind of abstract, glowing, philosophical essence. I'm talking about the essence that you perceive at the particular time in the frame of mind that you happen to be in. And when I say things, it's tempting to think that the analogies are between the things in the external world, but I really want to say that analogies happen inside your head, so that they're connections between two mental representations. They're connections between things inside your head, which we project to the outside world. And we say these things out there are analogous, and that's very reasonable to do.
most of the lineage for this reward idea can be traced back to Shane Legg and Marcus Hutter. I'd love to get them on the podcast, by the way. So if you know them, please invite them on. I think we'd have a great conversation, and they're pretty cool guys. But in 2007, they released this paper called Universal Intelligence: The Definition of Machine Intelligence, and it quickly became one of the articles of faith for modern deep reinforcement learning. Certainly by the folks at DeepMind and many practitioners. Their conception of intelligence is basically an agent being able to gain a reward consistently and summed up over the space of all of the computable environments, and inversely scaled by the complexity of each environment. Conveniently, their conception doesn't consider prior knowledge or experience or the information conversion efficiency or generalization. We already know from the shortcut rule that you get exactly what you optimize for at the detriment of everything else. If Kenneth Stanley was here right now, he would have a field day. If you haven't already, by the way, you should check out the episode we did with Kenneth Stanley. It was my favorite episode of the show. I mean, a reward is just an objective at the end of the day. Stanley hates objectives because of deception, because they're convergent, and because of the shortcut rule. It might be a slightly cynical reading of Stanley's work, but at the end of the day, Stanley effectively figured out that clever objectives, which is to say objectives which are impervious to shortcuts, deception, and convergence, he honed in on interestingness and its proxy objectives: novelty, diversity preservation, meta-learning, new objectives, and information accumulation, all of which could be optimized monotonically. Actually, Chollet figured out the same thing in a different way, right? The only objective in intelligence which can be optimized monotonically with no shortcuts is the generalization efficiency itself. We already know that you can't optimize monotonically on a reward signal without deception. Why do you think there's an entire literature in reinforcement learning about exploration? Honestly, I think the reward is enough paper is just complete madness. This is Francois Chollet.
In order to build a general intelligence, you need to be optimizing for generality itself.
So intelligence, which is to say generalization power, is literally sensitivity to abstract analogies. And that's in fact all there is to it. If you have a very high sensitivity to analogies, you will be able to extract powerful abstractions from little experience.
So anyway, this takes us full circle. The story of intelligence started with Minsky in the 70s, who thought that intelligence would arise from kind of compiling several statically coded task-specific programs. In the 80s, the story evolved to the current position, which is that intelligence lies in general learning ability, being able to acquire new skills through learning. This is still the dominant view now. But we're seeing hints of the next generation of intelligence, which is being able to efficiently learn new tasks or acquire new knowledge using what you already knew with abstract reasoning. We should also realize that with intelligence, the substrate and the context is important. Neural networks will never be able to extrapolate and will only ever achieve, at best, a glitchy representation of discrete problems. Intelligence itself might also be embodied or better thought of as an emergent process, which is far bigger than any individual brain. Anyway, I really hope you enjoy the show today. We've had so much fun making it. Remember to like, comment, and subscribe. We love reading your comments, and we'll see you back next week. Welcome back to the Machine Learning Street Talk YouTube channel and podcast with me, Dr. Tim Scarf, my two compadres, MIT PhD Dr. Keith Duggar and Dr. Yannick Lightspeed Kilcher. Now, our guests today are so incredibly accomplished as scientists and entrepreneurs that I could probably spend about half an hour just enumerating their numerous and impressive achievements. But here we go. Professor Gary Marcus is a scientist, best-selling author and entrepreneur. He is founder and CEO of Robust.AI and was founder and CEO of Geometric Intelligence, a machine learning company acquired by Uber in 2016. Now, Kenneth Stanley, who's one of my heroes of AI, was also one of the founders of Geometric Intelligence alongside Gary, which is super exciting. By the way, Gary was also listed as one of the top 20 most influential people in AI last year. Now, Gary is also the author of 5 books, including the seminal book, The Algebraic Mind, Klooge, The Birth of the Mind, and the New York Times bestseller, Guitar Zero. as well as the editor of The Future of the Brain and the Norton Psychology Reader. Now, he's published extensively in the fields ranging from human and animal behavior to neuroscience, genetics, linguistics, evolutionary psychology, and artificial intelligence, often in leading journals such as Science and Nature. He's perhaps the youngest professor emeritus at NYU, and his newest book, co-authored with Ernest Davis, is called Rebooting AI, Building Machines We Can Trust. I also highly recommend you read his recent paper, The Next Decade in AI, 4 Steps Towards Artificial Intelligence We Can Trust. Now, also joining us today is Professor Luis Lam, Secretary of Innovation for Science and Technology at the state of Rio Grande do Sul in Brazil. His research interests are machine learning and reasoning, neurosymbolic computing, logic and computation, and artificial intelligence, cognitive and neural computation, and also AI ethics and social computing. He was formerly Vice President for Research at the Federal University of Rio Grande do Sul in Brazil. He was Dean and Director of the Institute of Informatics, ex officio and elected member of the University Council at the Federal University of Rio Grande do Sul. He's a member of the program or organizing committees of a large number of international conferences and workshops on artificial intelligence, cognitive and social computing, logic and computer science, and embedded systems and formal methods. Lewis released his new paper, Neurosymbolic AI, the third wave, at the end of last year. It beautifully articulated the key ingredients needed in the generation of AI systems, integrating type 1 and type 2 approaches to AI, and it summarized all of the achievements of the last 20 years of research. Now, one thing I really want to get out of the show today is moving beyond the superficial. How exactly are we going to achieve a hybrid approach, conflating symbolic and connectionist methods? Let's take it as a given that a hybrid approach would give us models which have causal reasoning and are more interpretable, more robust, and more secure. Gary said in his Next Decade paper that without us, or other creatures like us, the world would continue to exist, but it would not be described, distilled, or understood. Human lives are filled with abstraction and causal description. I think this is so powerful. Francois Chollet the other week said that intelligence is literally sensitivity to abstract analogies, and that's all there is to it. It's almost as if one of the most important features of intelligence is being able to abstract knowledge. This drives the generalization which will allow you to mine previous experience to make sense of future novel situations. Anyway, Gary and Lewis, welcome to the show. It's such an honor to have you both on here. Where are we at with neurosymbolic methods?
Well, first, it's a pleasure to be here. It's good to be in an environment where people take for granted these questions, because I spent a lot of the last 20 years almost, or even more than 20 years, trying to get people to recognize the importance of abstraction. So I came to this having worked in psychology on children learning rules, and came into the first wave or second wave, depending on how you count it, of neural networks, and people trying to argue that there was no abstraction, that it was all just basically memorization through multi-layer networks. They were then 3-layer networks. And it's been a long, hard slog to get people to realize how important abstraction is. And I think that there's been a real sea change in the last couple of years. I saw, correlated with that is a lot of hype around AI with people who didn't recognize how important it is to get abstraction right, and thought, well, if we just have, a billion parameters, that would suffice. And in fact, even now you have a lot of naive people thinking the GPT-3 represents more progress towards language than it actually does. And so it's been really interesting recently to see people like Yoshua Bengio, who were historically fairly hostile to abstract knowledge and things like that, say, hey, we need to have causality in there. Of course, there have always been people like Ideo Pearl who have seen the value. And then to see Andrew Ng say, hey, there's too much hype in AI a couple of weeks ago kind of blew my mind, because he's been one of the biggest hypesters. I mean, he famously said, I can get a computer to, I won't quote it verbatim, but I can get a computer to do anything that a person can do in a second. And the reality is, even in a second, we use a lot of abstract knowledge, right? We use abstract knowledge about how the world works in order to interpret essentially every utterance. So I'm going to defer to Lewis on the state of the art in large part about kind of technical details of putting together neural and symbolic things in unified mathematical formalisms and things like that. I think he knows better than I. But I will emphasize one thing, which is that it's not enough to have a technical apparatus to be able to put these things together, and that we need to look at a larger context. And a lot of what the Next Decade article was that larger context. And so, there were 4 points in that paper. One of them was we need to have hybrids, and I actually cited an earlier version of the great paper by Lewis that you just mentioned. The recent version wasn't out yet, but Lewis has been a pioneer in that. But then I also emphasized abstraction in general and the value of it, which is, of course, part of why you want to have those hybrid models. And then I emphasized having large databases of knowledge and detailed cognitive models. So some of what I still see in the field is people working on the technical details where in some narrow domain, I've got an enormous amount of data and I kind of crush it with all of that data. But what's really interesting about human cognition is we can pick up new domains with relatively small amounts of data and interpret them. People are trying to crush these things with large amounts of data, but they're still doing it in this kind of anti-nativist way where there's no prior knowledge aside from what is acquired in the course of that system. And I think if you look at how people actually encounter things in the world, they have prior knowledge about domains and they can quickly assimilate new knowledge by building a model of what is going on and by having this rich database of, we'll call it common sense, sometimes it's expert knowledge. And so, for example, if you watch a movie and you see somebody pick up a gun, you know something about what guns can do. It's not like you're watching 30 seconds of the movie and then you infer that guns might kill people. You already know that, and you know some of the parameters, like the gun might get stuck, it might not be loaded. You might know the meta narrative. I think it's due to Chekhov that if there's a gun on the table, then you got to use it. In the plot, it's probably not just there for decoration. So you use that meta knowledge in the process of understanding things. And I have not yet seen any really rich reasoning system working at that level where it's all integrated. The closest thing is psych, which doesn't have the neuro side of things at all. I mean, I guess they're adding it in a little bit, but it fundamentally is a purely symbolic system and not a learning system. So there's still lots of things to put together. I think Lewis is working at the foundations of how can you consolidate these kinds of information at all. And we shouldn't lose sight of the fact that the larger context in which we want to do that is we want to be able to put all this knowledge together. Or right now, we're doing a video or podcast together, and so you have knowledge about like what's socially appropriate for that. I shouldn't get up and take off my clothes. It's not that kind of video. So you have background knowledge about etiquette. You have knowledge about what the audience that we're on the call with knows, what the audience out there in listener land might know. And we're constantly integrating just this huge range of knowledge. And we shouldn't forget that that's why we want to have the neurosymbolic integration, is to put together background knowledge. Some of it's going to be innate, and maybe we can talk about that later. Some of it's going to be culturally acquired and so forth. But that's the reason that we're doing this. So now I'll defer to Lewis to kind of give you the technical state of the art on how well we can do that with any knowledge at all.
Thank you, Gary. Thank you so much for the introduction too. And we are living at some, I would say, some exciting times in AI. One of the reasons is not the hype, as Gary mentioned, but I see that the times we're living are exciting because people like Gary or like Paul Smolensky and even Yosha Benjo, as Gary has mentioned, have now looked at what's going on and have noticed the need for abstraction, the need for interpretation, the need for better semantics. As Gary said, we had some very large language models that look very promising, that look very exciting when they go into the press, the media, the printed press, and so on, to the social networks these days, not the printed press anymore. And people get really impressed by some of the results. We can mention, for instance, the example, the exercise that The Guardian did in the UK by editing that small journal piece last year. And the editor said, well, I just put the same amount of effort, the same amount of work that I would dedicate to any kind of piece that The Guardian publishes. So that's the summary of what The Guardian did in some way. However, as we have defended here for quite some time, for a long time, as Gary said in his brilliant work on cognitive science and the way children reason, the way children learn. He has some very impacting papers on that and some books that are referenced to us in AI these days. We have to look at the foundations, and also we have to consider what kind of abstraction in AI and in computer science by the end of the day that we have to use. We cannot forget that computer science was born out of the symbolic school of reasoning, the symbolic school of logics. We don't need to mention Alan Turing and the pioneers, and the symbolic reason and symbolic AI has always been at the core of the kind of developments that we are dealing with these days. So when we see this kind of disputes or this kind of disparities that or this kind of separations or divides that we see in machine learning, we don't think that that makes much sense, or that this kind of division contributes to the development of science in general and of AI and machine learning in particular that are at the fore of this discussion. And when you think in terms of the kind of developments that we have been looking at over the last years, we are looking, yes, for a foundation of integrated logical reasoning and machine learning. Why this is important? Well, I'm sure that Gary will mention it later on. When we develop a system, an AI system or a machine learning system, we do not want only to find correlations or label classifications or better interpretation from the label databases that we have. We actually want to provide appropriate semantics for this kind of inference, this kind of reasoning that we are working on very large amounts, huge amounts of data, and this is only growing. And however, we cannot forget, and Gary has said that in several of his papers, we have also defended this position that formalizing notions like common sense reasoning or even combinatorial reasoning that is more related to the core, to the foundations of computer science is still a very, very open problem in the field. So what we look at in Neurosymbolic AI is exactly how to compute and how to learn with symbols inside or outside a neural network in the way that we can provide a proper semantics to what's going on in these very large language models, for instance, or in this very efficient, let's say, image interpretation and computer vision systems. But we do not have, at the point that we are in AI these days, a proper and a complete foundational semantics for the field. So what we look now here is how to provide a better semantical foundation, a better semantics for what's going on in machine learning, and also to explain how the reasoning process goes on when one is dealing with this very large connectionist models, with this very large neural network models. Because we have to consider that when one deals with millions and millions of labels, millions and millions of parameters, with the number of hyperparameters that one has to set these days, we look some side of the foundation, some side of what actually is going on in terms of rigorous semantic foundation that computer science demands from every field. So in terms of what we have achieved in technological impact, this has been impressive. There is no way that we cannot recognize that. However, when we see the hype in terms of claiming that the systems are better at language interpretation or language inference or language understanding or machine translation or language translation, we are still very, very far away from the kind of foundation that computer science and AI needs. So in this sense, I make a small comparison small historical, let's say, backtracking here. In the early 60s, at the height of the space race, there was a lot of investment in computer science for the reasons that we know. We need to put a man in the moon and bring him safely back. So there was a lot of investment in terms from DARPA, from NATO, from several bilateral government agreements in the Western world. And there was a lot of developments in computer science and computer programming. People needed to program computers much faster than using machine language or assembly language. So there was a lot of development in the 60s. And one of the developments that we had in the 60s was the search for a semantics of computing, the search for a semantics of programming language, what a program means, what the program was actually doing. This was extremely important if one considers and remembers the kind of hardware resources that we have at the time. We needed to provide a very adequate semantics, a very precise semantics, because it was a very high-risk project, put a man on the moon. So we needed logical and mathematical foundations. And at the time, there was this famous discussion between the computer science, the very prominent computer science in the UK called Christopher Strachey, who is a named professorship at Oxford University these days. Samson Abramsky is the Christopher Strachey Professor of Computer Science at Oxford now. And Christopher Strachey was trying to associate or to provide a formal semantics of programming language using a formal system called the lambda calculus, the lambda calculi. However, Dana Scott was a US logician who after that spent the next 10 years in Oxford, said, well, you are doing all wrong. The lambda calculus does not provide an adequate semantics for programming languages. We need to develop this theoretical semantics, a new theory to provide semantics for computing. So in the end of the day, they were able to provide a better formal semantics for programming languages, and now we have very effective programming languages that were very useful not only in the let's say during the 60s, but also later on. Today we know how to program. We give better semantics to programming languages and to the sense of computing. I expect to see the same kind of developments happening now in AI and in machine learning. We need to provide better semantics, better appropriate semantics, and this kind of results typically come from the logic community or the formal semantics community, come from also they get feedback from cognitive science, because we are dealing with learning here from neuroscience, but we are not at the point that we have a solid founded semantics for machine learning. And we need that if we want to provide not only a solid scientific background to our field, but also to make sure that people who are actually using, for instance, machine learning tools or AI tools in medicine feel that this kind of tools and technologies are safe to massive usage. So this is my introductory statement. I hope we can keep going on this subject.
Yeah, I mean, definitely covered a lot of territory there. And I think something that, Gary Marcus said in the beginning that I find somewhat ironic, there's an irony in the fact that it took so long to convince people that abstraction was necessary. I mean, after all, they're doing their research using abstract language. They're building systems on computers operating at a level of abstraction far above, the continuous wave functions that are governing the electrons, et cetera. I mean, all around us, there is symbolic reasoning, there is abstraction, and this is kind of a bizarre sort of denialism that this is all actually an illusion. And not only that, but it's not a very useful illusion, that we should just instead reduce all the way down to, continuous kind of functions. But I think a lot of that fear or resistance to kind of accepting that or the move away from it hinges on something that Professor Lamb said, which is that, we have to be able to optimize. We have to be able to search the space and kind of find workable solutions for it. And of course, we should all know that say discrete optimization problems, integer programming, et cetera, have this long history of being very difficult to solve because they have this kind of combinatorial nature to them. And I think it was in a debate with you, Professor Marcus, where Joshua Bengio said, Oh well, I can get kind of discrete reasoning by just having multimodal distributions and some type of sort of interactions between these multimodal distributions. But I'm wondering, the closer that they drive those kind of differentiable systems to emulate discrete or symbolic reasoning in some way, aren't they just going to then bring in all the difficulties and training and learning that we see if you try to just go ahead and operate at kind of a more discrete level of abstraction?
I think we haven't fully solved these problems, right? So what we want is to be able to harness the ability of these large systems to search large parameter spaces with all the value that you get from discrete symbol systems. If what you do is you take your neural network and you emulate a symbol system exactly, which you could do, we've known how to do for many years, then you're stuck with all the problems that symbol systems have had. If all you do is you emulate, a 6502 microprocessor and then, build the programming language BASIC on top of that, and then you write spaghetti code in BASIC, you haven't solved anything. I wish we had the answer right now, but I think the truth is we're sort of like, physics pre-Newton or something like that. We're missing some basic ideas about how to wrestle with the combinatorial complexity of reality, integrate the knowledge that we have about the world works with kind of learning systems. So right now, I could tell you I have a glass of water on the table, and you can set up in your mind the semantics of that. And Lewis might want to say a little bit more about how he's thinking about semantics, but I'll say as a cognitive psychology that when I tell you there's a glass of water on the table, that there's something in your head now that says there's a table, there's a glass, the glass is containing water, and you encode all of that, and now you can do some things. Like if you see me flailing around my arms, you might say, I wonder if that glass of water is going to be in trouble, and he might knock over that glass of water, and then you can make inferences. If he did, there might be glass on the floor, there'd certainly be water on the floor, it might make a noise, we might have to pause the recording while he cleaned it up. And so you can make all of these inferences, and you can do some of that statistically. And the confusion has come because the fact that you can do some of it entails in some people's minds that you can do all of it. So, if I fed that whole scenario into GPT-3, sometimes it would get it correct, but it wouldn't reliably get it correct. So if I said, he knocks the glass of water over with his hand and ... statistically, a likely continuation would be like, and there's water on the floor. And so you'd say, hey, GPT-3 has the semantics, it understands it. But when you push these systems, you quickly understand that what's really going on is it's like this giant library of cut and paste with a lot of synonyms. And it's just very superficial. It's not really building up a representation of where the glass is, where the water is, and so forth. The symbol systems are really good at doing that. I mean, we've had things like, Block's World for years and years that can make inferences. I mean, Block's World wasn't perfect, mind you. But the problem with those systems is everything's hand-wired in advance. In the next decade, I give this article of parsing the story of Romeo and Juliet with Psych. And if you have programmers who translate everything in the story into symbolic propositions, and you have background knowledge, like people when they're dead are no longer alive, like basic common sense, but encoded well, which is what Psych's project has been, then you can make great inferences that are really high level inferences about what Juliet might think Romeo's going to think when she drinks a fake potion, a potion that fakes her death, right? It's really fancy inference that people actually can make routinely. Everybody goes to Romeo and Juliet and they understand the dynamic that's going on of different people having different interpretations, and they understand the tragedy of it all. And so Psych can actually do that. But the problem is Psych can only do that when all this stuff is hand wired, and we can't sit around paying programmers to pre-wire every narrative that we might encounter. And so we need to bring these things together. I think a lot of it comes back to Lewis's point about semantics. The only way forward is to actually represent the semantics of whatever it is you're trying to absorb. Whether it's Romeo and Juliet or my moral tale of my glass of water or whatever it might be, you need to be able to manipulate the entities that your world is structured around and to track them. So I tell you there's a
Yeah.
glass of water and there's also a cat on the table, now you think about the cat and that's in your mental representation. And then you can worry, is the cat going to knock over the glass of water? And you make all these inferences. We just don't really have a technology that can do that in the full. We have technologies that can do that in the narrow. So, you can build some kind of, like a GPS navigation system does lots of inferences in the narrow, right? It understands, where the beacons might be, and it can make shortest path relative to some known constraints and so forth. So we could do this in the narrow, but we don't know how to do it in the general.
What's really interesting is that in the good old-fashioned AI days, we had human-captured knowledge, right? And we had the knowledge acquisition bottleneck, because I'm a huge believer in the kind of semantics you're talking about, and I agree that they can extrapolate a lot better. Although after the conversation with Chollet, I was somewhat convinced that there's an appropriate kind of substrate for an appropriate problem. So, type 1 might be good for MNIST. Although, interestingly, there's a type 2 abstraction for any situation. So, you can abstract MNIST into a discrete categorization. But I want to get to the nub of the difference between the GPT-3 fans and what you're talking about, because we spoke to one of our friends earlier. He was one of these differentiably minded connectionist, GPT-3 loving types. And Connor. And anyway, they think that it is statistics all the way down, and that we perform some kind of Bayesian update to data, with experience. And they think that there exists a universal generating function of the universe, and GPT-3 is somewhat akin to this. They think that any symbolic reasoning is simply an emergent phenomenon and a form of error correction, if you like, and would indeed even emerge in a larger version of GPT-3 if it existed. Even if this were true, in my opinion, it's a bit low down in the taxonomy to expect our models to memorize all the permutations of everything. It harks back to the ridiculous arguments about Turing completeness and universal function approximation and the need for infinite amounts of data and training passes, as you cited in your paper. When humans hear the statement about water leaking from a broken bottle, Gary, they can abstract and therefore extrapolate that information to work for ball bearings falling out of the bottle or dice falling out of the bottle. There's something critically important about being able to abstract information and acquire knowledge automatically. That seems to be the thing that we're missing, right?
I mean, absolutely, it's what's missing. I would say that your friend that you interviewed has a lot of buzzwords, but that there's no connection between those buzzwords and a working system at the moment. So it could be that many of those buzzwords really are part of the picture. So Bayesian updating, I'm pretty positive about. Differentiability is probably part of it. I don't think it's the whole solution. Nobody's really gotten all that to work. And there was another buzzword, emergence. And it's nice to say things emerge, but like GPT-3 is a really honest test of the hypothesis that's been kicking around for, depending on how you think about it, 20 or 60 years, of everything will emerge when I just feed in enough data. I mean, when I was in graduate school, Jeff Ellman was writing these papers about simple recurrent networks that in many ways foreshadow what's going on right now. He's no longer with us. I sparred with him many times. He doesn't get nearly enough credit for having anticipated all of this stuff 20 some years ago. The first thing I did after graduate school was to have a debate with him at MIT about simple recurrent networks, and the same issues are still kicking around. But we have a mind-boggling amount of data compared to what he was working with. He had like 600 sentences that maybe he'd handwritten or not that he fed into this proto multi-layer neural network, and it could predict certain things about grammaticality, basically. So subject-verb agreement. And it had its limits, some of which I pointed out or whatever. But we had a little back and forth. But now you have gigabytes of data instead of like a few K of data. And it's gotten so much better in some ways and not at all better in others. So which ways has it gotten so much better? Well, his system was like cat drink water. It was like, it was like telegraphic speech or that we talk about in child language literature. It was nothing like real language. But he was right to see in that you could emulate language if you had more data, and that there were regularities that you could capture. And he did, interesting analyses about the clustering of sentences. And I made the counter argument. I said, even when you have these clusters of sentences, that doesn't mean that the system is truly abstracted. If you have a new sentence, it's going to have trouble. And I did some formal demonstrations in a 1998 paper called Rethinking Eliminative Connectionism that he has anticipated so much of what's going on. And, one of the things I said was there are problems with same different. There was just another paper came out a few days ago I haven't read yet showing same different problems in the context of current neural networks. So 20 years later, even just the basic notion of same and different is hard. If what you're doing is you're accumulating a lot of things, that doesn't mean that that they're similar, doesn't mean that you actually understand the abstract principle that underlies them. And if I can just give a little philosophical terminology, philosophers sometimes talk about extension and intention. And intention is, I think, close to what Lewis means by semantics. So extension is like, I show you, I tell you what a pair is in cards, let's say, and I show you 2 2s, 2 3s, 2 4s, 2 5s, etc. And you just have the list. You look up in your table, a 9 matches a 9. Great, now I know. That's the extension of a pair in cards. The intention would be like knowing I've got 2 cards that match. And by and large, what these neural networks do is they traffic in extension, things that have appeared together and clustered together. The intention is understanding the deeper reality that is causing it such that you can generalize it. Well, we're still kind of stuck there. It's just the extensions have become massive, and so they become more compelling for certain things. They become more compelling in this prediction thing, but you can always break them. So, I had this example in Technology Review with Ernie Davis where you're drinking cranberry juice and you're really thirsty. You don't quite have enough. You pour in some grape juice, and what happens? And GPT-3 continues, you drink it, which is a plausible continuation, and then it says you die, which is not plausible because nobody dies from drinking cran grape juice, right? And so it doesn't really understand the toxicology of human beings, even though it pretends like it does when it says you die, but it doesn't actually understand anything about those mechanisms. And so the extension has led it astray in that case because there's not much left. You're really thirsty correlates in its database. I'm kind of being a little bit loose here, but correlates in its database with sentences about you die. So lots of times when you drink something out of desperation, maybe you die from it because, or in its database, like people tell tales of, adventurers or who drank the poison or whatever. That's a fact about its database. And maybe that's another way to put all of this is these systems are totally driven by these kind of idiosyncrasies of the database because they don't represent the intention. Just the way with my pair example, like if you happen not to have had 2 10s, if that's all you did was a lookup table, then you're in trouble when you get to the 2 10s because you don't really know how to think for yourself. And semantics is about being able to think for yourself at that level. And so, what's better is the emulation you get from the extension is so much better because we have, training sets that are approaching a terabyte. And so you're much more likely to find something in the extension that's close to the thing you need. And there are some places where that has practical value. If you wanted to make an autocomplete system, then that's awesome, right? It's going to make the best autocomplete system that you can imagine. But if you wanted to give medical advice, and somebody tried to set this thing up as a suicide prevention counselor, then it's a tragedy, right? There's an example out there on the web where someone asked GPT-3 or said, I want to kill myself. And GPT-3 said, I think that would be a good idea. Like, this is not what you want. Like, it doesn't understand the underlying conceptual framework of a suicide prevention hotline. It just randomly putting together sentences that seem to be close to its database. And even with a terabyte, it's not enough. So you go all the way back to John Locke, and the idea was, hey, if I just have enough sensation, it will all, and this ties back now, it will all emerge. I don't know if Locke used that word. I can't remember offhand, but your friend with the buzzwords is like, it will all emerge when we have enough data. Well, no, it will emerge when we have enough data and we have a formalism that allows us to put together the symbolic knowledge with the kind of large-scale quantitative data in a way that can contact a cognitive model and allow you to do reasoning over it. That's when it will emerge. But that is to say, we need a bunch of tools there that we don't quite have. It's not going to just come out by magic. GPT-3 was the test of the magic hypothesis. Put it all in with, a reasonable structure, transformer network, and hope for the best. And what you get is a mess.
I think the argument to make of we need abstraction, we need sort of semantics to describe it all it's an easy argument to make, but how do you being in this field, arguing for this, what's kind of a workable definition of abstraction? Like, how do you, going also here beyond the buzzword of, we need abstraction. I do abstraction, you do abstraction. Like, when does a system do abstraction, and what would you accept? Like, if I came to you and said, I have GPT-4 and it does abstraction, what would you accept as a test that is happening?
I think the proper tests aren't being done right now. And I think there's a related problem that people have finally gotten wise to, which was actually at the core of the 1998 article, which is about extrapolating beyond a training space. So the core example that I used there was actually about same different. It was, I'm going to train you on the identity function for even numbers of a certain size. And I'll give you some examples. And then there's going to be two kinds of generalization you can do. Interpolations, like you've got a cloud of points I've trained you on. Can you interpolate between them? And yes, neural networks can do that. Not perfectly. There's a bunch of problems, but reasonably well. And then there's extrapolations. Like I give you an odd number, and is represented as binary digits. Well, the odd number is outside of the extensional space. It's outside the training space of what you've seen, or the training distribution. And that kind of system can't generalize. And humans do generalize, or generalize in this particular way that I would say is the abstraction kind of way, in the same circumstance. So I followed the 98 article up with a 99 paper in Science with 7-month-old infants. And I showed infants do the kind of generalization or abstraction where they treat something as a class. So what I gave them was set of sentences like, and I had some collaborators, I should say, my team and I, we gave people examples like la ta ta, ga na na, to be of an ABB structure, let's say. And we'd either give you something, all new words with the same structure, wo fe fe, or a different structure, wo wo fe, which would be an AAB structure. And we balanced a lot of stuff about phonetics and stuff like that, so that you couldn't just rely on phonetic overlap. We did a bunch of controls. And the study has replicated, which is not always true in psychology, but this one has. And what we found is the kids recognized change to a new structure over new material. And that's what that's really the essence of it. That's what it is to generalize, extrapolate beyond a training distribution. And I think that's really what abstraction is about. It's to say, I get it. This is identity, or identity over time. So, the first one was identity with I was literally describing identity. So f of 110 is 110. And then the second is identity over time, basically. So I have AAB or ABB. And that is the course, to be able to do something like that. Of course, it's not just identity. In fact, what I described in the 2001 book, The Algebraic Mind, was a whole family of functions that I called euquotums. I don't know if I've ever said the word out loud or not. Universally quantified one-to-one mappings, UQOTOM. It's been a long time. It's been 20 years. So there's a whole family of things where each input has a unique output. And it's not that I think those are the only things you can do with abstraction, but those are the ones that are most cleanly cut away from the things that you can do with other kinds of systems. So the scientifically purest case are the ones that require you to take a one-to-one mapping. Every input has a unique output, and generalize that outside the training space. So we can do that. So you can do f of x equals x for any number. You can do f of x equals x plus 1 for any number, x plus 2, right? There's an infinite number of these things. You can think of language in the same way. So like I can add ed to any morpheme and I get a new past tense. So I can say, this is glass clothing, and I've just glass clothed my laptop. I don't know if you could see it. So I've made up a new verb, and you know that you're going to add ed to that thing, or maybe it's glasses cloth, and then I've glasses clothed it. And so you can play this game perpetually. You don't need to have it in the extension of what you look at. And there's a little cheat having to do with phonetics, which we ruled out to show that it really is generalization outside the training space the kids could do. That's a working definition of a form of abstraction. It's not the only form, but that's the one where the neural networks keep getting into trouble over and over again. And it's really foundational. There's so many things that we know. The Latin for it is mutatis mutandis. We know that this thing is true for, but I'm going to change a little. So I'm going to say, walk is walked, talk is talked, and mutatis mutandis, glass is clothed, or glasses cloth goes to glasses cloth, right? We know this kind of, I'm going to change it with respect to this item. That is a, pretty clean version of abstraction that we don't have an adequate handle on. I mean, there's some technical machinery now that can do it in little narrow cases. You want to be able to do that in general. I mean, here's one way we would know that we're making progress in AI. Would be there's this huge database, free, to which I frequently contribute money, not time, called Wikipedia, which of course you all know, right? Human knowledge that is in written form, so machines in principle could read it. The reality is all that machines can read right now are the boxes, right? So what year was somebody born? What is the population of Canada, and so forth. We get machines to do that. That's not hard at all. We suck that up into Google Knowledge Graph and so forth. But the unstructured text in Wikipedia contains, much more than any individual human knows. And we should be able to suck it up. If we really had AI the way the newspapers tell you did, then we would be leveraging that. We would be able to use that to make advances in material science or figure out new ways of manufacturing vaccines or whatever it is we wanted to do. So there's all this information. It's there for the taking. And the proof that we don't have AI is nobody has any idea whatsoever how to actually take that beyond really superficial things like, playing Jeopardy by finding the title of the Jeopardy question that most closely matches a Wikipedia page. Because most Jeopardy answers are titles of Wikipedia pages. So we can do that, but we can't actually have somebody read this stuff and figure out how the world works. Whereas, my 7-year-old can read, Wikipedia and learn something.
I think this is the key thing, though. I agree with you that abstraction it's almost synonymous with generalization. And you cite the example in your paper, Gary, about the scalar identity function. I think it's a beautiful example. I cited it on the show the other week, which is that you can't generalize even outside of the training range. And you went a step further. If you train on the even numbers, you can't even generalize to the odd numbers. It's a sorry state of affairs. And as a human, we would look at this. It's a bit like an intelligence test. You're trying to find the obvious pattern that will work outside of the training range. And maybe there's some Occam's razor. Maybe there's some core knowledge or prior knowledge that needs to come into that. But to us, it's absolutely obvious what the pattern is. But to a neural network, it's not obvious. Now, Chollet, I think, has the best articulation of this concept yet. But I think actually, after I read your paper, you were saying pretty much the same thing many, many years before, Gary.
Except when I tried to publish it, just as a brief historical footnote, one of the reviewers said I was doing a terrorist attack on neural networks, and it was not relevant.
Well, no, I think what's fascinating about this is the concept of, so the brittleness depends on the type of the problem, right? So, neural networks are brittle for computing the digits of pi, and symbolic methods are brittle for a computer vision task like MNIST. So you make the argument, Gary, that we need to have a heterogeneous AI that kind of enmeshes these two things together. And another thing I noticed reading both of your papers is that, you get a lot of flack, Gary, but I think you're a moderate. The kind of recommendations you're making are already normal. If you look at a lot of undisclosed hybrid methods like AlphaGo or even GPT-3, in my opinion, has a discrete input, a discrete output, a discrete search on the top of it. So these are continuous models in the inner loop with a kind of discrete search or some kind of discrete concept in the outer loop. We're already in the paradigm of hybrid models, aren't we?
I wrote this other paper we haven't mentioned in 2018 called Deep Learning, a Critical Appraisal. And the take-home message was that deep learning was one tool among many, that we needed hybrid models. And Eric Brynjolfsson, the economist who I think has done the most for sort of thinking about consequences of AI, immediately tweeted about the piece, and he said that, it was really provocative. And Jan LeCun flexed his weight and said, well, it might be provocative, but it's mostly wrong. And then his followers all attacked me on Twitter. You can go back into the archives. Everything that I said in there, I believe, is now actually received wisdom 3 years later. So I was brutally, repeatedly, frequently attacked for saying that these systems don't abstract very well, that there's a real problem with extrapolating beyond the training data, that replicability was a problem, that there's no real semantics there. Etc. I don't remember all 10 off the top of my head. I think all of those are now actually received wisdom. They're now, in fact, if you watch Bengio's recent talks, they're basically the introduction to his talks are those things that I said. And LeCun has turned around, and even a year ago, or a year and a half ago, I was attacking GPT-2, saying that it doesn't reason very well. And he tried to say you're just talking about number problems. I said, no, it's a more general problem. And he said, well, you're fighting a rearguard action. We solved this at Facebook 3 years ago, and he posted a link. And then I could never even get the source code for the paper. And I mean, it's not solved. And now, so even he has actually turned around, and he's the one who brought to the world's attention the GPT-3 suicide example. So he is now, he's all about common sense and how these big language models don't cut it. So even like my fiercest critics have actually turned in the last couple of years. Yannick said it kind of amused me a minute ago. It's easy to make the argument about semantics. Well, no, it wasn't. For 20 years, every time I made it, I was accused of being a terrorist and a bad person, whatever. So it's not easy to make that argument. It's easy to see it in hindsight. And I always think of the Leo Szilard thing about the 3 stages of scientific truth, which is it's wrong, it's not important, and we knew it all along.
But we do need both approaches. So there is a lot of data does fall.
Coming back to what you said for a second, it is actually the moderate view to say that there is wisdom in these two traditions. There aren't always. So, creationism versus Darwinism, I have no patience for creationism. I do not think there's wisdom in that tradition. Sometimes when two sides see some value, one of them I think is just off. I don't think there's there's a kind of emotional wisdom maybe in creationism, but there's no reality to it scientifically. But a lot of times when two different sets of people see value in two different things that are trying to approach the same problem, there is actually value in both. And that is the case here. Going back to 1940s, there has been clear value, or I mean, even earlier on the symbolic side, there has been clear value in symbolic computer science, right? All of the world's software pretty much is still built on it. You read these like press releases about how we're going to get rid of programmers in favor of machine learning, but I won't say it's bullshit, but it's really far from reality. That is not how you build a browser or a web app or whatever. I mean, sure, you might do perception with a neural network, but the basic logic of your system is in logic. Every computer language is just logic. So you've got people who said, hey, this stuff might be really valuable for AI, and they're right. And then you've got these people that say, there are these problems that are not amenable to that because there's all this kind of statistical stuff that isn't naturally captured, although you can actually integrate it in symbolic stuff. And there's this other way of thinking about things, and it's really good for pattern recognition. And they're right. Going back to McCulloch and Pitts and Rosenblatt and so forth. Like Rosenblatt was right. He built a neural network. It was featured in the New Yorker in the 1950s. It said it was going to change the world, and it kind of did. 65 years later. So like, there's something to both of those traditions, but because like grant money is at stake, people have been kicking each other for years and years, saying, "No, give me all the grant money. Don't let my friends have it. They're doing something different." And so there's been this hostility for literally 65 years that has not served the field well. And so like people like Lewis are trying to like step beyond that and say, yes, there's something here. But there is this historical context where people want, their students to get the money, or they want the grant, to get the big jobs or whatever. And it's led to this incredible amount of hostility. And then you have people like Hinton, who once saw the value of the integration and then saw the value of like the hype and the I don't know, I shouldn't dig too much into him, but he wrote a great book. Lewis can tell me the year, or I can try to get it, 1989 or something like that, on neurosymbolic integration. It was an edited volume, I think, for the journal Artificial Intelligence. And then in recent years, Hinton has had no patience for the symbolic side at all, saying, we don't need this. His recent paper, Glom, which actually said some nice things about the Tech Review, is really interesting, but it's like bending around in crazy ways in some ways in order to not use symbols. So the question that the Glom paper is really trying to deal with is, how do you get a network to uniformly represent parts of things? Well, the obvious answer is to use symbols and label those parts, which is, has in some parts of the world been useful. And he's doing everything he can to avoid doing that. And maybe there'll be some success there. I mean, as he says at the beginning of the paper, this is like a theory and not a model. It's not actually an implemented model. I think it's the first sentence of the abstract or something. But, I actually think it's interesting to try to think through those questions because none of us have the answer right. So looking outside the space of the answers that we have is the only way to succeed. The space of answers we have is not adequate. It just isn't. And so we got to look somewhere else. And so I admire him for trying to do that and not getting sucked up in the, can I beat MNIST, by another 1/10 of a percent or ImageNet by another 1/10 of a percent, which is what most of the research does. It does not take us to what is the new idea here that we need. And so, I like the paper in that sense. On the other hand, I think it's tying itself into not saying, I don't want to use symbols here. And he's got this like very weak paragraph at the end. I sent him fan mail for the first time in my life. And I said, I agree with everything in the paper, or I find the whole paper, really provocative, except of course, I do not believe for a minute the argument you gave against symbols, which was hardly an argument at all. I can't even remember what it was. But so, he's still like pushing with all his might to try to exclude the symbols. And I don't think, there's value in that any more than I think there would be value in the symbol of saying, give us big computers and we too will, succeed and we won't need the neural networks. We actually need both, and we need ideas that we don't have yet.
Absolutely agree. Yeah, absolutely agree with Gary on this point that we need both.
So, Tim, that is the moderate view, is that we need both. Lewis and I are the moderates, but we're not viewed that way. I mean, we're viewed as like, cantankerous curmudgeons holding on to the past. We're not viewed as the moderates who are trying to find room for everybody.
It's all extremely sensible, as I said when I was surprised actually. But I do want to stress though that there is if intelligence is generalization, there are types of generalization and abstraction which you can only achieve with neural networks. I mean, just look at the manifold of human faces, for example. Try and create that generalization.
Just for 1 second. For a visual, you do this like kind of MTV style, right? Video style. You're going to cut it together. There's a maybe I can dig it up for you. A headline of reporting the Bengio debate that says Gary Marcus is the villain AI never needed, and you should throw that in there in some way.
Excellent, we will.
It's a cool title to have, right? I mean, like that's something you write on your autobiography. Going back from the past a bit to the future, and Lewis, what you said before, talking a lot about kind of we need the ability to semantically describe what we're doing and so on. If I think of today really getting down to how do I implement a neural network, right? I say, here's my input data, right? And then I do Keras or something. I import some module. I do layer, right? And then I put a loss function. I put an optimizer, and I run Go. So, if you can outlook to a world that you would like to see, how do we need to change this in order for us to be able to better semantically describe what we want to do with these systems?
That's a very good point, Yannick. Let me mention something about relations and what's going on in terms of what you said. In a very simplified way, we touch on this point in our paper. We have this so-called embedding techniques these days. We mention it in our paper, so we wrote about it, where one transforms the symbolics representations into vector space. But this is for implementational purposes. We just discovered, I don't know if Gary agrees, that it's very efficient to use tensor products and so on, and linear algebra, and this kind of algorithms that have been very effective. Okay, but this is an implementation strategy, as I say. This is not proper a proper semantic foundation for deep learning. Promising that the approaches that people use these days, technically, they have the so-called embedding techniques, where they seek to translate the symbolic representations or the symbolic information to vector spaces, where the reasoning process or the implementation of what people call reasoning takes places via matrix computations over distance functions. And in these systems, the embedding, let's say, is carried out using backpropagation typically, or some form of modifications of backpropagation, which is still very popular, which is still used these days. And in this way, what people are seeking is a kind of a manual translation or manual way of representing relations in a distributed neural network. In a distributed neural network that is seen as tensors or matrix computations and so on. Another thing that people are doing these days that perhaps, I say perhaps, will shed some light in how to have better abstractions is that people are starting or are using the so-called graph neural network models. But in the end of the day, a graph can be seen as a relation, right? You can translate graph knowledge or graph neural networks into relational forms. And relational forms or relational representations are, in the end of the day, a form of predicate logics, first order logics. And this can be translated or this can be related to the kind of work that people did for 40 years in databases, in relational databases. So there has been some very interesting work by Alon Halevi from Facebook now. He used to be at the University of Washington in Seattle. He came from the database community, from the foundations of database community using Datalog, which is a kind of extension of Prolog to deal with databases. And he's now analyzing how to build these neural databases, these deep learning databases and so on. So I, in this sense, I'm kind of optimistic in seeing that people are noticing the connections, people who work on the foundations of science and foundations of AI. And these people are very, very serious people that they have a lot of respect for the symbolic world. They are seeing and analyze the connections that we have now between, say, matrix computation, linear algebra, tensor algebra, graph neural networks, and relational work, and the relational work in AI. And when one looks at relational reasoning, that is the reasoning and the learning that people are after in AI. Even in deep learning, people want to discover relational information, want to discover relations between objects in scenes, in movies, in language, in image interpretation. All this machinery, all this formal background is in symbolic AI. You cannot ignore that. When you look at the history of computer science, as Gary said, even McCulloch and Pitts, when they provided perhaps one of the first neural network models, one of the things that they showed in the paper was how this kind of networks they proposed carried out Boolean reasoning, logical reasoning. If you look at the paper, Gary, right?
Yeah.
And they were cognitive scientists, right? They were looking at the forms that neural networks could in the future perform logical reasoning. They were, let's say, the first neurosymbolic, Gary. The first ones that were neurosymbolic were McCulloch and Pitts, who are, let's say, the forefathers or the godfathers of neural networks, if we have this sense or this definition. So what I see now is an opportunity for people to realize that it doesn't make sense to say that symbols are useless, because they are not. We just celebrated 50 years of perhaps the most influential paper in the history of computer science, which was the paper by Stephen Cook on NP completeness. In the beginning of May was when the paper was published. Can we ignore symbolic computing in computer science? Absolutely not. Are we going to prove that P equals NP using deep learning techniques? Probably not. We are going to use symbolic machinery. We are going to use combinatorial techniques, combinatorial reasoning, common sense reasoning in building the proofs, inference, and so on. So I don't see the reason to be a divide. I'm very happy that some people from cognitive science, some people from the symbolic AI world, and even some people that come from theoretical computer science are starting to work in this field and analyzing the connections between symbolic reasoning and machine learning, symbolic reasoning and connectionist models, deep neural networks. We can also look at the work from people like, as I mentioned, Alon Halevi, people like Martin Grohe, who is analyzing the logic underlying graph neural network models, which are quite popular these days and highly effective in representing some combinatorial problems and learning about combinatorial problems and so on. So I believe that in a few years' time, maybe 5 years, we will have a much more adequate relationship between the communities, let's say, where people will respect more each other, right? And we're also going to see more and more connections between the results that we have in databases and the results that we have in database theory, the results we have in logic, in computer science logic, and the results that we have in deep learning. So in this sense, I never saw the reason for this sometimes not very kind debate between the two communities. And I believe that computer science, the way computer science was born, if you take, for instance, the work by John McCarthy, the work by Alan Turing, and the work, not to mention the work that the cognitive science McCulloch and Pitts did already in the 40s, the symbols were there.
I think one day a social psychologist really should examine kind of the history of this acrimonious relationship, because I mean, to Professor Marcus's credit, we've been reviewing all this material, right, in preparation for today, and he's been very consistent. And one thing that I think was quite disingenuous of some of his opponents is not only do they really try to stay out of his side of the field, at all possible contortions, but they also move the goalpost to kind of subsume like his area and now claim it's what they've been talking about, for kind of all along, right? I think that's quite disingenuous. But you mentioned a trigger word for me, which is sort of NP, the problem space of NP completeness, and the space of NP or NP hard problems often arise almost all the time when you have these sort of discrete problem spaces, right? Like the traveling salesman, where you have to make kind of discrete decisions, or the 3-SAT problem, or integer programming. So again, we're coming back to this duality, right? We have kind of almost the wave particle, discrete continuous duality. And as you've both said, nobody solved the problem of how do we do optimal learning or even efficient pragmatic learning in the space when it involves this discrete sort of symbolic paradigm. I'm kind of wondering what you both think right now are the most promising directions for that. Like, we've talked to some of the program synthesis community, like sort of Dreamcoder. Professor Lamb, I know you have some recent papers on as you mentioned, like the graph neural networks. I mean, I think there's a lot of options out there. Are you seeing any type of convergence or areas that we should be spending a lot more time on that are kind of being overlooked right now?
I think you too wrote a song about this called "I Still Haven't Found What I'm Looking For." What I'm looking for is not just, I think, in the end, or so let me say it a different way. The right solution here is probably going to be both an algorithm and also a large knowledge database. And I think what people are looking for is an algorithm and trying to duck the large knowledge database question. So, the person who most went after the large database question was Doug Lennon. And nobody outside of psych is particularly happy with what he came up with. My view is that he was trying to do something great. He didn't succeed, but that what he was trying to do is vital. And I wonder if we had the right algorithm, but we didn't have knowledge in a machine interpretable form, whether it would be that useful, whether we would even know. Like, maybe even we have it now, but because we try to use it in a void, in some sense, in this very empiricist, I'm going to start learning everything from the data kind of way, it never really amounts to that much. So I often think about this paper by Rich Sutton called The Bitter Lesson. And in Sutton's paper, the argument that he makes is every time we try something, big data wins over knowledge. And I think he is right as a historical matter that has been the case. But what I think he leaves out is that as a historical matter, we've only solved a tiny fraction of the problems that we hoped that we would solve in AI. That most of the problems that we hope that we would solve in AI have not been amenable to either a knowledge-based approach or to a big data-based approach. So, for example, the problem of language understanding is basically unsolved at this point. whatever hype aside. It's basically unsolved. And it does not appear to be amenable to big data. And in fact, I mean, this is another way of making the hybrid argument. It needs something beyond what we have. And so if we had the right hybrid algorithm, but we didn't have the knowledge to go with it and the kind of cognitive structures for how you build mental representations over time, if it wasn't part of a fuller, richer system, I'm not sure it would make a difference. And I'm not sure we would know. I'm trying to think of an analogy here. Like, it could be that a 3-month-old baby actually has the innate knowledge, the right cognitive system, but they don't have enough common sense knowledge acquired through those mechanisms yet. So in fact, the 3-month-old infant has one of the best minds on the planet. No non-human will ever match what that 3-month-old is about to do. Its potential is enormous, but if you sat there and did psychological studies, you'd say, okay, great. If I do a study right, it has object permanence, and Piaget was wrong about that. But you'd also say it really doesn't understand beans about what a laptop is for, and it doesn't understand, how to assemble an IKEA kit. I guess it's not passing my benchmark, so let's toss it out, right? And if you had that magic formula, but it was uneducated, you'd miss it. We really need a full system, and building that full system includes going after Lennett's problem of what large-scale knowledge you need to have in accessible form and how. It needs to go after the problem I keep talking about, but not enough about, which is the cognitive model problem, which is as information comes in, how do you assemble that into a database? So yeah, people talk a little bit about knowledge graphs and stuff like that, but we really need a rich answer to that. So how do you build a mental model of, let's say, the people that are on this call and their motivations and stuff like that? Until you have that, you might actually not know it. That you've solved this other piece of it. So one theory is maybe it's already been solved, but nobody notices. And you could ask, what are the most promising things? I think in general, people that are trying to say, how do I use prior knowledge to affect learning, are at least asking the right question. I'm not sure they're asking it in the right way, but I think that's the right question. Is if you know something about something, you shouldn't just start from scratch. And of course, convolution is the greatest version of that we have, or one of the greatest versions. I know that the world is orderly, that, the thing over here and the thing over there are likely to be the same, essentially, right? I mean, it is translation invariance. That's a piece of knowledge that we integrate in a learning system. But we don't have, as far as I know, a general answer to that. A bunch of people in physics, for example, are thinking about that a little bit in narrow cases. What if the prior bit of knowledge I want is that objects move on paths that are connected in space and time, right? So you can't just wink in and out of existence. The Star Trek transporter doesn't really exist, right? That's as an example of a piece of prior knowledge that's relatively easily stated. Every physicist knows is essentially true at the medium object level. We won't get into quantum stuff. How do you put that, let's say, into a neural network of some description that is going to watch the world and be able to tell me which are the individual entities here? How are they going to leverage that in their segmentation system, let's say, to be able to parse out the world and understand paths and stuff? Like, that should be a solvable problem. And we should, in 2021, actually have an off-the-shelf technology where I can, somehow encode that knowledge and then put it into my learning system. I would say I haven't found something that lets me do that in a comfortable and general way. And so I'm not satisfied with what's out there. Maybe someone's written about it and, it's not getting the attention it deserves.
Yeah. I think enmeshing the symbols and the deep learning models, that's challenging. But from my perspective, the reason why Go5 failed in the 80s was because of the knowledge acquisition bottleneck and the brittleness. I even see this now. There are companies out there that are building large-scale knowledge graphs, and there's just never enough knowledge. You just need more and more knowledge, and it's almost as if the knowledge we captured before didn't seem to work. We need more knowledge for a slightly new situation. The first problem, just quickly, the first problem is that we need humans to capture the knowledge. And I'm thinking, well, what are they doing? Well, I think the best way to think about what they're doing is, when you do computer programming and you do object-oriented design, you design classes and you design inheritance hierarchies, and you take two objects together and you say, well, what do these objects have in common? Well, they're both animals, they both have fur, they both have legs, and you're designing these abstractions that generalize really well. And we need to have an AI that can do that automatically, right?
Yeah, I mean, going back a sentence or two, it takes a lot of knowledge to do much of what humans do. So you think about, I don't know, a 13-year-old watching a movie. They've been on the planet 13 years acquiring knowledge constantly. So I have well, soon we'll have a 7 and 8-year-old. I have a 6.99 and an 8-year-old. And, they spend most of their time acquiring knowledge of some form or another. This week it's chess and spies. Those are their hobbies. And so they're learning, like, what do spies do and what's a pin in chess and stuff like that. They're sponges for abstract knowledge and concrete knowledge of all sorts. Some of it's metrical. How do I do a cartwheel? But they are constantly accumulating knowledge. And by the time they get to the point of doing many of the things that we expect, they've been doing that for years and years. So, like, why should we think that it's a quick fix? I don't think it is. I think, it's going to be a lot of work. The nice thing about software is, and this was Lennett's thesis, which might still be true, even though I don't think he's succeeded, is it might be worth, like, several thousand people hours, or people years even, in order to do this once, because once you've done it, you can percolate it. And everybody takes that argument for granted in driverless cars. They all assume, yes, it's expensive, but when we get there, the value will be enormous, so it's worth it. And very few people talk about that with respect to knowledge. Like, N of one. Lennett's the only person who still kind of says, it's really worth it to accumulate this database. And he's been doing it for 30 years. I think he's put in 1,200 person years or something like that. Back of the envelope, 1,500, which is a lot, but it's, it's not that much compared to what it's taken to build. I don't know, Google search is a lot more than that, right? And so, like, it's a lot compared to what an academic can do in their lab, or maybe what a startup can afford to do, but it's not on the global scale that big. Maybe you need to do that before you get any of this off the ground, but maybe we need to do it in a more modern way using techniques that Lennett hadn't thought about when he started this in the 1980s. But maybe it's unavoidable. I mean, my strong suspicion is that it is a bullet that we have to bite, and that nobody wants to bite it. And so everything suffers as a consequence, because what we do, since we don't have machine accessible knowledge that would take a lot of work to develop, what we do is we try to trade it off with these massive databases drawn from Reddit, which, brings all the kind of bias and anti-vax nonsense and so forth with it, and is not actually distilled enough to really be all that useful. And, sometimes the harder approach actually turns out to be the right one. It's like guitar instructors have this saying, slow is fast and fast is slow. So the field is taking the fast approach of, I'll get all the data, I'll put it in this big thing, and I'll be there. But it doesn't really work. It ends up, in the long run, it's not actually taking us to the deeper answers. The slower approach would be, let's do the hard work of one by one, taking some of these important priors. Josh Tenneman is the only person I know who's really trying to do this. Of trying to take a prior like spatiotemporal continuity and figure out, how would I put that in with the rest of my system? And maybe if we can figure out a few of those, we can accelerate the process and it'll get faster and faster. But we might need to do some really hard work on some basics like that of, how am I going to represent just the minimal kind of physical reasoning about the world and psychological reasoning. And, maybe each one of those pieces is going to be like a PhD thesis to get one fact. And that is going to be so depressing compared to, I raised ImageNet by 1% in 6 weeks of work by twiddling this parameter of connectivity. Nobody wants to do it.
Sure. Yeah, and you might win a Turing Award by figuring out to incorporate one form of invariance, efficiently into machine learning. I really want to pull in Professor Lamb on this question too, but I know that I believe, Professor Marcus, you have a hard stop in about 4 minutes, correct?
Or 2, I think.
Okay, thank you so much for being here. It's
Thanks,
really
it's really
been
fun.
An honor.
Thanks a lot for your questions. Great seeing you.
Professor Lamb, I just wanted to follow up. So we've gotten kind of Professor Marcus's take on, look, we've got to build this knowledge base and also find ways to incorporate prior knowledge. I'm really curious what your take is on some of the most promising avenues and perhaps even overlooked avenues for finding a way to more seamlessly integrate, continuous and discrete activities, symbolic reasoning with perception.
Yep, that's a good point. That's a very good question. let's say when we think in terms of relational learning, learning this structured relational domains, like for instance, let's think for a moment for instance, of a database. Is sometimes very hard because this kind of discrete relations technically they lead to gradients that are not very easy to deal with in neural networks. So there is a lot of challenge in representing relations because of this technical, let's say, this technical challenges that we have to deal with in neural networks. And for instance, when we confront, let's say, images or signals, they are in a way they are very appropriate for neural networks in terms of pattern recognition, in terms of finding relations and correlations and associations between this kind of data. However, when we deal with relations and natural language, it's a kind of data where we find a lot of relations between the structure of the sentences in terms of the grammatical structure of language. This become a kind of a very challenging challenging problem, and this is why many people have stated that in spite of having this very impressive large language models, we're still a long road. We're still very far away from having natural language understanding, proper natural language semantics. And someone was saying here how you define semantics, how you define a formal semantics for language. And this, of course, uses tools from logic, uses tools from theoretical computer science, and in linguistics and in formal semantics and in the philosophy of language, we have to provide an account of the meaning of how you compose the parts of sentences, the parts of texts. That's why this is so difficult to do in very large language models, because you find the correlations, you find the proximity, you find the approximations to kinds of bits of text that are related to the queries, but you have no formal definition of how one thing relates to the other. So this is one thing that's very hard. And this is a well-defined research subject, research community as well in logic and computer science, but that we're not being able so far to translate the results from this community into natural language understanding, for instance, into natural language inference. And in deep learning, when we think in terms of the successes that, for instance, DeepMind has had with AlphaGo, AlphaZero, they have some symbolic component. It's clear that they have some kind of symbolic component in their systems, and they are doing, as Henry Kaut said at AAAI 2020 in New York about a year ago, in February 2020, they are doing some form of neurosymbolic reasoning, neurosymbolic learning. And this tension that we have between learning and reasoning is a tension that has this long history in computer science. But I also like to state a sentence that Professor Les Valiant, who is a Turing Award from Harvard University, who is also a British computer scientist, Les Valiant has said that, well, this tension between learning and reasoning go as far back as at least Aristotle. Because when you think in terms of the syllogistic arguments and the inductive arguments that Aristotle used more than 2,000 years ago, we already had this tension between, let's say, deduction and induction could be could be seen as a kind of learning procedure.
The interesting thing about semantics, because we speak with Walid Sabah, who's a linguist, and he says the biggest problem in language understanding is the problem of the missing text, which is that almost everything that we mean, we don't say. So it's all very well having the semantics, but understanding seems to be something. It's another module that we need to have on top, where we reason over world knowledge and we do a whole bunch of other stuff. So where does the rubber meet the road between that understanding problem and the semantics that you're talking about?
That's a good point. We have a lot of contextual information here. We have to think, let's say, what I like about when we think in terms of the possible world semantics, it's not very related to that, but I'll get to the point here. is that you start to analyze the similarities between the possible situations that we have in the world, let's say. So in this way, when we are trying to interpret language and there is a lot of unknowns or things that were not said, we have to think in terms of how to interpret the possible world in which this kind of utterance, this kind of text, this kind of sentence was written about. So this will be a component. And here we have an advantage of these very large language models, because when you bring a lot of information, perhaps the next step is to bring also to the fore the context in which this kind of text was written, historical information, temporal information about the text, about the language that we are about to interpret. So the advantage here about having a lot of data is that not only you bring the textual information or the sentences, the utterances, the questions, the summaries that we have, you also bring contextual information. And so in this way, one could perhaps think in terms of, let's say, for an analogy here, not only in terms of a Montague semantics that is very classical semantics in natural language, but we also could bring about perhaps the kind of models that computer scientists brought to the fore that are based on the possible world models in terms of branching time, in terms of words that are more similar to the other, words that are related to the other. So if we can bring this kind of information, I believe we are getting closer to having a more appropriate semantics, a more appropriate semantical models for instance, large language models or other tools that will be developed that we cannot even imagine at this point. So that's a very good point that you brought to the debate. And another promising thing that I want to mention here is that if we think of the history of deep learning, we say, well, in the early 2000s, I used to go to the New RIPS conference. And I remember that when I went to the New RIPS, that was called NIPS conference in the early 2000s, and we once presented a paper in 2003 about neurosymbolic temporal reasoning about knowledge. And I remember that one guy came to our poster presentation. He said, look, you are one of the only guys here who is using artificial neural networks, right? At the New RIPS conference. Virtually nobody is presenting a paper on neural networks at New RIPS anymore. Why are you using neural networks? Apparently, only you and Jeff Hinton here are presenting papers about artificial neural networks. That was just 3-5 years before the deep learning revolution started in the academic community, and let's say 7-8 years before the deep learning revolution came to the foreign industry and in media. So when we think in terms of symbolic AI or neurosymbolic approaches, perhaps we're at the same point in history. We showed in the late 90s, in the early 2000s, that there were symbolic interpretations, there were kinds of symbolic reasoning that could be performed by connectionist models, by neural network models. I believe that with the recent developments in integrating the hybrid models, the symbolic school and the connectionist schools, we perhaps, as Gary said before he left, that perhaps the best results are in some of the papers that were published yet, but we have not been able to exploit to their full potential.
I was listening to a podcast with Thomas Mikolov. You probably heard of him. He's the guy who created the skipgram model. And he said that before the skipgram model, it was like the dark ages in natural language processing, right? And there are other perspectives. So we know a lot of linguists and logicians, and they say we're in the dark ages now. They say that we're on a hiding to nothing with this vector-based approach to natural language processing. It's antithetical to understanding. He says that there are 0 degrees of freedom. Natural language understanding is about uncovering the single human thought behind an utterance. It's a binary. It's there. Do you know what I mean? So they think that we're in the dark ages now. And you are very much a pragmatist, and you're halfway between the two things. Because language, to me, it seems like a very discrete problem. Doesn't seem like we should be using vector spaces here at all. So what do you think about this?
I think language and natural language processing, natural language understanding and relational learning, they are, let's say, associated. They are related in the sense that they are both discrete. They are both structured in a way. We know that some people claim that language is not that structured, but we have a formal grammar for most Western languages, let's say, or a formal semantics or a semantics understanding for most Western languages, let's say. So language, in a way, is structured, and the structure sometimes is very strongly correlated to discreteness, to the point that you are making. So in this sense, the hardness of building deep learning approaches that are very good at relational reasoning in the logical sense, in the symbolic sense, is akin to the challenge of building deep learning systems that can produce language interpretation, language reasoning in the same way. So these problems are related. So what I believe and what I guess here, and I'm not sure because they are both hypotheses, is that perhaps the neurosymbolic approach is promising here because we have better tools to translate, say, the knowledge that we have about language into a neural network, into a neural network model, or we have better tools coming from the logic world, from the logic in computer science school. We have better ways to build this hybrid approach where the network interacts and the network provides information, or the network learns discrete structures. So what we do in neurosymbolic AI or neurosymbolic computing is not to throw all the data at the same point, let's say, not to feed a very huge, very large neural network with an even larger amount of data. What we do is we do some pre-processing. We provide knowledge representation tools to proper design a learning system where symbolic structure, discrete structures are first learned by this machine learning mechanism, and from this learning ability, and then you verify, then you do your cross-validation, then you use your statistical approach to validate what you have learned. So the challenge here is to design these tools to combine the discrete nature of language, the discrete nature of relations, and the continuous characteristics of the neural network approaches. And what we also have to add here is that we do not only have to think about neural network learning. We can consider perhaps reinforcement learning as deep learning has done over the years. They have been considering reinforcement learning and other learning procedures combined with neural learning to have better learning machinery, better learning results, and in the end of the day, the best, very impressive technological tools that they have. And I firmly believe, and what we have seen over the years, is that if you are able to have a better representation for your discrete structures, and you train your learning algorithms with this translation that you bring from the symbolic world into the neural network world, you have better learning procedures that perhaps will be able to learn about symbols, let's say. Let's focus on symbols here, but also to learn about logics, to learn different kinds of logics and different kinds of reasoning. Let us not forget that we humans are not very good at logical reasoning, right? We are much better, let's say, at perceiving, at seeing, at informally understanding sentences, at informally understanding information about our world, but we are not the best at performing logical reasoning, logical inference. And typically, if we can teach our computers, teach our deep learning machinery, or teach our neurosymbolic AI systems, then we probably have we'll probably have to solve one of our biggest problems, one of the biggest challenges, that is to provide, let's say, logical reasoning to the masses, logical reasoning to everyone, logical reasoning to make inferences about what we are expecting about the world. Not only in terms of logic, but to analyze hard problems. For instance, when you have disputes between companies, disputes among social groups, disputes about several kinds of problems that we have in businesses. Perhaps if we can feed the AI systems with a lot of information and then to design the proper inference mechanisms, or making the computers to learn the proper inference mechanisms, then we will have the tools to provide us with better logical information about how to take decisions. So that's another advantage of the neurosymbolic techniques. Yeah.
Could I challenge on that a little bit? Because you said that human beings often aren't very good at reasoning. And by the way, because you folks talk about robust AI being a good thing, but if you're talking about creating learning agents, then in a way it's quite worrying if they might be acquiring knowledge and reasoning on new knowledge, and who knows where it might go. But in a sense, you could argue it both ways, right? So natural language understanding is about disambiguating out of the 50 possible meanings of an utterance to the intended meaning. And actually, I mean, you know, when you say the corner table wants a beer, we know the corner table is a person. We hardly ever misunderstand each other. It's something which is so invisible that we almost never misunderstand each other. But then you could make the other argument that there are loads of situations where people really do have bad reasoning, especially if you're having political discussions on Twitter. You know, God, if only they thought the same as me.
What we are able to do as humans is to consider a small set of arguments when we talk to other people. We typically do not add a lot of information when we're dealing with logical reasoning, with formal reasoning, okay? However, when we are dealing with one of our fields of expertise, say music or football or any other field of expertise, we have, as Gary said here, years and years and years of information that we have acquired, that we have processed, that we have memorized, that we have revised, that we have formed our sets of beliefs, that we have also made some belief revisions on what we used to believe, and so on. We have years and years and years of information about our domain of expertise. And this is a lot of information that's stored in our brains, in our minds. And of course, we are able to reason upon our field of expertise much better than about other information that we don't know about. This is related to System 1 and 2 from Daniel Kahneman, but that he explains in his book, that we are very able to react to things that we have seen in the past, react to, for instance, to information that is related to our survivability, like fear, for instance, and other situations where we are threatened. And when we specialize in some field, we are also able to react very quickly. So there is an interplay between System 1 and 2 that are the quicker one and the more reflexive one, and so on. And however, when we are dealing with logical reasoning about new information, about new propositions, new statements, for instance, that someone makes at a social network, we tend to have some deductive reasoning that sometimes is not quite elaborate, because we also mix some information, some contextual information that we react to the provocation, let's say, that we react to the emotions that are involved in the system. And sometimes we are not able to do the proper logical analysis of the situation and to find out more information, more data about to take a decision. So we are very good at doing logical reasoning about our domain of expertise, but we are not very good to doing a logical reasoning about domains that we are not experts on. And since most people are not expert in mathematics, in logic, in natural language understanding, natural language semantics, we have not also been able to translate this kind of information, this kind of knowledge about language, knowledge about the mathematics to the deep learning systems, to machine learning systems. What machine learning systems were quite effective, were very efficient, were very good at, were to use a lot of data, I mean huge amount of data, and find correlations, find inference about image interpretation, about language inference, and so on, from this huge amount of data. But we cannot say, mimicking ourselves, that we are that these machine learning systems are reasoning upon the data and are actually giving us information that has a solid foundation about, for instance, natural language understanding. So in this way, I compare the developments that we have in deep learning to the developments that we have in our formal education. People are very good at their domain of expertise. They accumulate a lot of data about this domain of expertise, and they can very quickly respond to questions about football, about music, about impressionism, about French painting, and so on. However, when we ask them about other things, other domains of expertise, we are stuck. So when we compare deep learning or compare the current AI tools with this situation, it's more or less related to that. It's not exactly related, but it's an analogy that I use, for instance, with my students. Wow, why deep learning systems are very good in image processing, image understanding, finding correlations in images, finding relations in images. Then I explain how labeling works, how the basic algorithms work. And I also explain, let's say, the importance of having a lot of data, about a lot of labeled data about particular domains. In this way, machine learning system and AI system will work very well. As, for instance, when a human expert has accumulated a lot of data, a lot of information about his domain of expertise, about 2-3 decades of working, or about hard work. Yeah.
Do you feel that? Because I really want to get to the root of this. Is reasoning a first-class citizen? You know, like we're talking about symbolic reasoning. Is it a first-class citizen in the human brain? Do you really believe that, or do you think it's some kind of? Because you know when we talk about it and we project it as a kind of calculus, right? And it makes sense in that domain. But do you think it's first class in our brain?
Reasoning is a first class citizen, but reasoning is also based on experience. It's also based on learning, right? For instance, let's take a mathematician or a logician. He has years and years and years of practicing proofs over examples. He's like a deep learning system who has seen like 10 million proofs, 10 million complete logical proofs. Then he becomes an expert in reasoning about proofs, reasoning about logics, reasoning about a particular domain of mathematics. His experience comes not only from his biological composition, comes also from a lot of experience, a lot of hard work on seeing patterns, on seeing examples, on seeing sentences, on seeing logical inferences, on seeing different proofs in books, on developing these kinds of proofs. In a way, reasoning is built in. Reasoning is a first-class citizen, but it also depends on how you interact with the world and how you draw your own inferences from the world. Of course, if you practice less, if you use less learning algorithms about your reasoning system that feeds your reasoning systems, perhaps you are not very sophisticated in reasoning. But depending on how much you have developed your expertise and how many examples you have done over your life, you become better and better at reasoning. It is a first-class reasoning, as learning is a first-class reasoning.
Well, we often have. I think I'm taking this a bit out of what Keith usually says, is that if we look at the human brain at a basic level, it is neurons and cells, and we all agree that humans do reasoning, right? Humans, well, maybe not we all agree, but we all here agree that humans do reasoning. We can manipulate symbols in our head. So I think maybe what Tim was getting at is, do you think that there is kind of like something special about the brain? There is an extra module that we have for reasoning, or can this type of reasoning actually be implemented on the substrate, on like the same substrate that does the pattern recognition, or are these two different things?
That's a great question. I believe we actually have only some small evidence about this thing, but the answer is that I don't know. I don't know how it works because we don't have enough evidence at this point. So from as far as I understand from neuroscience, I'm not a neuroscientist, but as far as I understand, we don't have enough evidence about if they are either integrated or separated. what machine learning people like to think and believe is that we have these distributed representations and distributed forms of reasoning going on. And this is a good point. This is a good point to consider in terms of not only of from a computer science approach, but also from a cognitive science approach to think and consider that we actually do have distributed knowledge representation, distributed symbolic representations, and distributed reasoning going on in our mind and brains. That's a good point that needs more attention and needs more neuroscience research to confirm or to refute the hypothesis that we have at the moment. So I don't think we have 100%. We are 100% sure about if this is either integrated or separated, or if it is distributed as many people from machine learning currently believe. Yeah.
So sometimes we kind of expand on this question a little bit because even if you leave aside kind of the neurophysiology behind, we can think just in terms of abstract properties. Is there something missing from the artificial neural networks that we're playing around with today that we could, if we just borrowed it and abstracted it a little bit and stuck it in there, it might open up new paradigms or new capabilities? So for example, some people think it has to do with asynchronous firing of neurons, that we need to be able to have kind of a processing that can take place in the neural network so that some neurons can fire over here and then actually at a subsequent time influence neurons that are back further in the network, or having mechanisms that sometimes feedback and mimic like what the dendrites can do, where they can build up like a charge, if you will, that can cause like a different type of firing. So for example, maybe you want to have multiple activation functions that can trigger differently or even simultaneously. Yeah. So there's like a lot of, you can speculate about a lot of different kind of abstract capabilities that if you could add them into the artificial neural networks we have today, might enhance its computational capabilities, or maybe increase its efficiency at certain computational tasks. So I think we're just kind of wondering, what abstract capabilities do you think might be the most promising, if any?
Well, there seem to be some very interesting results coming from, for instance, from this new transformer models that use some attention mechanisms that have been very effective in some applications, definitely in sequence modeling, in language too. So this seems to be promising, but since it's relatively new, if you compare these models with the models that the convolutional models that Jeff Hinton, Yann LeCun used in the early 2010s to let's say to feed the deep learning revolution, we will need more and more results and more test beds coming from, for instance, from these new architectures. I like the idea of exploiting, extending, and analyzing the graph neural network models, because graph neural network models, they are very good at representing relational structures, and in this way there are hope for us that we are going to be able to learn discrete or structured relational domains that are considerably that they are harder to do these days. So Keith, I believe that the architectures that exploit the possibilities of graph neural networks, and as a consequence, a kind of relational model or relational neural network that someone will come up from drawing. Someone will draw inspiration in graph neural networks to come up with some kind of relational neural network. This can be very useful in terms of relational learning, and in the end, it might be very useful in language understanding, machine translation, and having a better semantics for language, because once you have a relational neural network or a relational representation of language or a relational representation of sentences and texts, perhaps we are getting closer to having a better semantics for natural language understanding. So I would bet not too much money, but I would bet that these relational models derived from graph neural networks are a good avenue of research for the coming years, because of their proper proper representation of relations, and relations are a very important structure in computer science and in natural language too.
Excellent. Well, Professor Louis Land, thank you so much for joining us this evening. It's been an absolute pleasure. It's
been fantastic. Thank you, Yannick. Thank you, Keith. Thank you, Tim. Thank you to Gary, who has just left us. So it's been a pleasure. And let's stay in touch. Let's stay in touch with developments in machine learning, AI, and computer science. So it's been a pleasure. And thank you so much for hearing someone far away from South Brazil. Thank you.
It's been our pleasure.
Been our pleasure.